Okay, good morning. So I would like to welcome all of you, the students and the participants, and also the lecturer. And so I declare open the ceremony of the SIMPA Research School on Singularity Applications. And of course, to make it possible, we need to ask help for everyone, all institutions. And I'd like to thank firstly the CAPS, PROEX, INCTMAT, Foundations Composition Mathematics, IMO, and SIMPA, and also the General Consulate of France in São Paulo. And now let me introduce some local and international authorities. And first of all, I'd like to introduce Ms. Nadège Mézier, from Science and Technology Advisor of the Consulate General of France. And just do a sign, please. Okay. Professor Mihai Tiba, University of Lille, coordinator of the SIMPA Research School. Okay. Ms. Rosanne, researcher at India, France, scientific officer at SIMPA. She's right there. And our main host, André de Carvalho, professor and the head of the ICMC. He's right here. Thanks for coming. And okay, I'd like to request the authorities to say some words to the audience to welcome all of you. First, I would like to ask Professor André de Carvalho, as I said, the main host today. Please.
Thank you very much, Raimundo. Bom dia, good morning, bonjour. It's a pleasure to welcome you all to the SIMPA School, Research School, and to ICMC. ICMC, the Institute of Mathematics and Computer Science, has a very strong group of singularities, which started with a former director, Professor Lobel, and then had a very strong growth with Professor Maria Aparecida Ruas and Professor Favaro. So all of them had some role in the management of the institute. Professor Dean was vice director. Professor Favaro and Lobel were director of the Institute of Mathematics and Computer Science. Let me say a few words about ICMC. ICMC started as an Institute of Mathematics Science. It was originated from the São Carlos Engineering School, and it's one of the 42 research and teaching units in the University of São Paulo. Have two big units associated with mathematics, here in São Carlos, ICMC, and IME in São Paulo. And the University of São Paulo also has some museums. One of them is the Paulista Ipiranga Museum, which is in the Independence Park, with associated celebration of 200 years of Brazilian independence. Coming back to the event, I saw that we had a very rich number of activities in the next almost 2 weeks. So I wish you all a very pleasant stay in São Carlos, in ICMC. So you are all most welcome here, the participants, including the students, the foreign visitors, and to be very nice, very great pleasure to have you all here in São Carlos, in ICMC. Thank you very much.
Okay, now let's move to the online authorities. First of all, I'd like to introduce Ms. Nadège Mézier. Please go ahead.
Thank you very much. Good morning to everyone. I'm really happy to be with you today. So I am in São Paulo and I couldn't come to São Carlos. I have some slides. I don't know if you see them. It works? Yes. All right. Now it works, yeah. So I am Nadège Mézier. I am attaché for science and technology from General Consulate of France in São Paulo. I will present you what we are doing in science and technology really quickly, and about the cooperation between France and Brazil in this area. So we have a long-term cooperation in cultural, scientific, and academic. The Consulate of France in São Paulo is not only the only one in Brazil. We have the embassy in Brasilia, and we have 4 branches, one in Rio de Janeiro, the other one in São Paulo, the other one in Recife, and one in Belo Horizonte. In Belo Horizonte, there is no consulate, but we have someone who works on cultural, scientific, and academic cooperation. We have 4 Franco-Brazilian schools, one in Rio de Janeiro, one in São Paulo, Natal, and Brasilia. We have 35 French alliances, Alliance Française, where people learn the French. We have 4 Campus France agency spaces. Campus France is an agency about mobility, international mobility of students. And we have 4 representations of research organization, French research organization, which are CNRS, Institut de Recherche pour le Développement, IRD, CIRAD, and INRAE. All works have researchers in Brazil. What do we do in the scientific and technology cooperation in the embassy and the consulates? We act as focal point for Brazilian and French partners, ministries, governments, universities, research institutions. We are doing a science news bulletin every month. We are financing of research projects in collaboration with Brazilian stakeholders, such as CAPES, for example, or FAPESP. We have bilateral programs, student exchange. We have academic chairs in Rio de Janeiro, in São Paulo, in Minas Gerais, and later incoming in northeast of the country. We have activities on dissemination of science and research with seminars, conferences, podcasts. We are organizing networking events too, and we have special projects related to the France-Brazil border with the French Guiana. We have also programs really strong now, which are on the climate, AMSUD, which is South America climate. There are programs with France and 10 Latin Americans, including Brazil. The objective is to reinforce network research, Latin America network research on climate. We have the same with information and communication, and with mathematics. And we have a program which is called PREFALC, which is France with other Latin American and Caribbean, and it's about to reinforce seminars in master's degrees. I think I lost one slide, which is not here, but I will speak for you. It's about other programs too, Brafitech and Brafagri, which are mobility program, exchanges programs on engineering degrees and agronomic and veterinary studies. We have CAPES Coffee Cube and USP Coffee Cube. Sure, some of you know about them. There are programs on mobility for missions for researchers, but doctorate and postdoctorate too. We have something I lost? No, I think it's what about? We have fellowships for masters and co-tutel doctorate. And I wanted to finish with a focus on cooperation in mathematics. Can you put the, yeah, thank you, the slide. So as you know, France has a tradition of excellence in mathematics. We have 13 field medals, the last one with Hugo this year. And the University of Paris-Saclay is first in mathematics in international rankings. France have a long-term cooperation and strong links with Brazil on mathematics. Since the 40s, 50s, we can speak about André Weil, which has a position in mathematics in USP. During 2 years, we had Laurent Schwartz, first French to receive field medals, who stayed various times in USP, collaborating in the Instituto de Física and Physics Institutes with Carmen Liz Ribeiro Praga. And Laurent Schwartz loved chasing butterflies in the forest of Tijuca. During the 70s and 90s, young French mathematicians performed their military service as coopérants at the IMPA, Instituto de Matemática Pura e Aplicada, in Rio de Janeiro. We can talk about Pierre Bérard, Étienne Guis, Jean-Christophe Yocos, Christian Bonatti. And in the IMPA, there is a Unité Mixte Internationale, UMI, IMPA CNRS, with the name now of Jean-Christophe Yocos, to remember him, who died in 2016. And this UMI give fellowships for 1 year for French mathematicians to stay in the IMPA. So each of the countries, France and Brazil, is now a major scientific partner to the other in the field of mathematics. We can remember too the Fields Medal Award in 2014 to Arthur Villa, who holds a dual appointment at IMPA and at the University of Paris, now Université Paris-Cité, but I saw that he is in Zurich now. And this Fields Medal awarded to Arthur Villa is a great token to this partnership between France and Brazil in mathematics. So I wish you all a really pleasant and a great research school in mathematics. And thank you, everyone.
Well, it's me to speak. So, yeah, so I do I continue? Somebody introducing me or not? No. Raimundo. Yes? I'm online. I'm in the air. Okay, so let me introduce myself. I'm Mihai Tibar. Could not come because of medical reasons, and I'm sorry for that. I'm disappointed not to be with you, but I'm at least online, and I want to thank you all, the organizers of the courses and all the lecturers who in particular made big efforts to provide beamers and videos last year. You can see the webpage program 2021 for some of them now. And I want to thank the 2021 team and especially Anne Friedrich-Krüger for installing and managing the IT platform that was used last year and still works. I want to thank the organizers of this live meeting in San Carlos, a long list of persons, and special thanks to Maria Ruas, that we all call affectionately Sidinia. Now, for all participants, I will be very short. For all the participants, but especially for the beginners, young people who are here, please, well, young is not well defined. Please allow me to start telling a story. It is about a young student, like many of you, not very motivated for the canonical studies in the school, writing poetry, not attending too many classes, and preferred the nature. In his 6th year of college, he was kind of forced to take a supplementary course in order to complete his curriculum. By some curiosity, he took the one delivered by a Japanese visiting professor in Seoul at that time, whose name was Heisuke Hironaka. Quite improbably, but our student fall under his charm. And from that moment on, he started to enjoy mathematics, and in particular, singularities, a topic in which Heisuke Hironaka had got his Fields Medal in 1970 for the famous resolution of singularities in characteristic zero. I wish I had more time to continue this story, to tell this story, but I will be short, and maybe some of you already guess who is that student. Let me now divulge his name and invite you to find more by yourself, for instance, in Wikipedia, and its source is listed there. I have some preferred sources and links which I put in this speech, in the written version of my speech. His name is Jun Hu, and he is one of the 2022 Fields medalists. The Fields medals were just announced earlier this month. I think that Dirk Siersma and Laurențiu Maxim will tell you more about Jun Hu in mathematical terms this time. Jun Hu, the one who thought of being an interviewer, is now interviewed. In particular, there is one interview where Jun Hu speaks about Milnor numbers. And I give here in my text version the link to that interview and to his paper, which has the same, the title about Milnor numbers, for which I'm now proud to have been one of the referees who recommended publication at that time. Enjoy this meeting. Thank you.
back here. First, I'm happy because it's the place where I graduated from many years ago, which I'm not going to say how many years were, but many, many years ago. And where I started to learn mathematics from professors as Andres said before, like Professor Leubel was my professor. And I learned a lot of him, but especially from Cidinha, who was my first advisor in the research. And then it's very, very nice to come back here. And I really like to thank her because after all these years, I'm still doing this mathematics. As it was said before, I'm a scientific officer for SIMPA. And I want to tell you what SIMPA is. SIMPA is the International Center for Mathematics, Pure Applied Mathematics. Is what we call in France an association, which means that we're getting financial support from the French government. But since, let's say, 10 years, we also getting financial support for all these countries that are mentioned here, like Norway, Deutschland, Germany, Norway, Spain, and Switzerland. And it's located in Nice, which is a nice city in the south of France, and has some executive board and a governing board with people from all over the world. They're all very nice people, as you can see from in the bottom left. And we had some scientific council, which is scientists and mathematicians from all over the world that decide on which research schools like this one are going to be hold actually in the 2 years. So the basic principles is to have some, sorry, I just put the timer so I don't talk too much. So there's the basic principle of SIMPA is to develop and collaboration with the mathematicians and the institutions from all over the world, especially from the developing countries. And the main activity is the research school as this one, but we're also doing courses online, courses from like say 3 months in Africa, for instance. And we have schools in partnership, which means that some other institutions are actually organizing this. And we have SIMPA fellowships that allow students coming to France, for instance, to have some semester in Institut Henri Poincaré, for instance, if you have a thematic semester. And the way it works, I know that you've seen this poster before. And then this is just the way that schools are organized. That you have just if someone wants to organize a school, you contact a colleague from the country where you want to organize the school, and then you have to discuss with a scientific officer, like myself, and building a project. And this is you have to find, of course, all the courses and build a scientific program for that. And this is just these are the scientific officers. My colleagues from France and from everywhere, in Spain, for instance. And the proposal is submitted to scientific council, which is going to evaluate this proposal, and then is either validated or not. And this process takes about 2 years. So that's why we should have been here last year, but then you had to postpone because of the pandemics. And but at least we're here now, so we're going to take advantage of this, that you can actually be here. So just to finish this, you can sign up for the monthly newsletter, and you can also apply to become a SIMPA member. And as we can see, these are the new members for last year, but you can also apply, you have new ones from last beginning of the month. So basically, SIMPA is trying to help people and students from all over the world, especially developing countries, to try to continue and progress in mathematics. And that's pretty much it. Thank you very much, and I wish you a very, very good school. Thank you.
Okay, thanks, Rosane. So now some very important few announcements. Please, inside any building here in the CMC, we need to use the mask, okay? And so during the registration, maybe you got your badge, right? So to get into the building 5, which is right here on my right, and building 4. To reach the building 4, if you go, if you get out, get left again, you stay in front of the building 4. Any of this building, you need the badge, okay? There is a electronic control. And what else? Okay. And sorry for late. We got some problem in the microphone. We need to extend, and we lost more or less 15 minutes. But I think it's time to start our school. Please enjoy it.
Não cai não, né?
Okay. Okay, let me introduce the first lecture. It will be held by Roberta and Bruna, and they will talk about complete intersection with isolated singularity. Please enjoy it.
Thank you, Raimundo. I'm just going to say a few words about our mini course, and then Bruna will give the first lecture. First, I would like to thank the on behalf of the 5 lectures of this mini course, I would like to thank the organizers for this opportunity. So, the first part of this mini course was given last year during the online section of the SIMPA school. And at that time, we studied hypersurface. I mean, the set of zeros of a holomorphic function germ, Cn to C. And we've seen that the Milnor fiber has a homotopy type of a wedge of spheres, and the number of spheres is called Milnor number. And it is an invariant when you do change of coordinates in the source. So this right equivalence group provided an algebraic method to study classification and invariance of singularities. And this second half of the course, we want to generalize those ideas for ICES Isolated complete intersection singularity. Bruno will define it, but roughly speaking, is the set of zeros of, here I see, sorry, hypersurface. The set of zeros of holomorphic map germs. And here the contact group provided the algebraic approach. And then now Bruno will show us the contents of the lectures. Thank you very much.
Thank you, Roberto. I don't have the thing to change the slides. Here it is. Good morning, everybody. Thank you. First thing I want to say is I'm sorry to my colleagues from the mini course. I should have put in all names here. I didn't realize that it was going to be here for so much time. Sorry. So we will have 4 lectures. The first one is today. I will do it myself. We will start with some basic results of local analytic geometry that we will use on the other lectures. Then I will give the definition of ICES and the definition of the contact group and the notion of co-equivalence of map germs from Kn to Kp. Here K could be the group R or the group C. The field R or the field C. And the main result is that two map germs F and G are co-equivalent if and only if their local algebras, which we call QF and QG, are isomorphic. In the lecture 2 will be given by Maria Aparecida Soares Ruas and Roberto Alvicatic. If you guys want to say hi, show yourselves. And this lecture is about the finite determinacy and versatility of unfolds of maps for the contact group K and map germs from Kn to Kp. So they will make the infinitesimal criterion of finite K-determinacy, which say that F is finitely K-determined if and only if its K codimension is finite. The geometric criterion of Matter-Gaffney. In the complex case, finite K-determinacy is equivalent to that F is finite to 1 on its critical locus. The complete transversal method. And the R parameters unfolding F is versal if and only if it is transversal to the K orbit. Oh, and also they will give some consequences about the relationship between K versatility and A stability. The lecture 3 would be done by Juan José Núñez Ballesteros. Juanjo, say hello. It's about versal deformations of ICES and the topology of the generic fibers. So Juanjo will restrict himself to ICES given by a fiber of a K-finite map germ from Cn plus K to Ck. He will give the notion of versal deformation of the ICES. He will say that it's strongly related to the K-versal unfolds of F, the map. He will do some properties of the discriminant of a versal unfolding. He will say the link and the Milnor vibration of an ICES, then the Milnor number, and also a theorem of Gaffner and Hauser, which is a criterion to prove that 2 ICES are isomorphic in terms of the modules of infinitesimal deformations. And the last lecture would be given by Terence Gaffney. Terry, do you want to say hello? We will define the witness condition A and B, and also the Verdier's W condition. He will give some basic definitions and properties about integral closure of ideals and modules and their connection with Singularity. And also we will give an application to characterize the Whitney singularity of families of ices in terms of the multiplicities and also the constants of the mixture sequence. Okay? So now let's start with our first lecture. I don't know how much time I have until the interval. 15 minutes. Okay, if I'm going, you please tell me, Raimundo. Okay, so the first thing we will do is to see the local ring ON. The first definition I need is the definition of German function. So I will consider two real or complex manifolds that I will call N and P. The dimension of N is N, and the dimension of P is P. And I will take a point X in N. And I say that two smooth maps defined in a neighborhood of the point X in N into P, F1 and F2, where is the thing to point? Here. In this way, are equivalent if there is a neighborhood, which I call U of X, which is a subset of the intersection of U1 and U2, such that the maps, they coincide restricted to U. Well, a germ of map, or a map germ, is an equivalence class by this relationship. And I also denote a map germ in this way. Here I put an X and P, the image of X by a representative. So, given a germ, the derivative of it is the derivative of any representative. And I say that the rank of the germ is the rank of its derivative. When the rank is the dimension of the source, I say that the map is immersive. When the rank is the dimension of the target, I say that it's subimmersive. And the map germ is singular when it's neither immersive nor subimmersive. And I say that it's a germ of diffeomorphism if one of the representative is a local diffeomorphism. Then, by the inverse function theorem, a map germ X is a germ of diffeomorphism if and only if its derivative at X is an isomorphism. Well, I need to define how I compose two germs. If I have a germ F from NX to PI and a germ G from PI to MZ, to define the composition, I need to choose good representatives, good for me. So the composition is the equivalence class, the germ of G tilde with composed with F tilde, where the representatives is does that. F tilde of the U that I choose here has to be a subset of V. Well, we know that two germs, we know from the first course, the two germs F1 and F2 are equivalent if there exist germs of diffeomorphism, H and K, like this, H in the sources and K in the targets, such that this diagram commutes. And we can see that Nmap germ is equivalent to some germ from Kn to Kp. Then we consider only smooth map germs from Kn to Kp. Finally, the definition of the ring. So I denote by O and P the set of smooth map germs from Kn to Kp. When this P is equal to 1, I put O and X, to say that it's the set of smooth map germs from Kn X to K. And also, when this X is 0, I just don't write this 0 here, I write On. ON is a local ring, whose maximal ideal is the germs which takes 0 to 0. Just for remember, a local ring is a ring which has only one maximal ideal. Okay? So this is the definition of our local ring. I have to have some water. Okay. Now with the germ of complex analytic sets. So first, a locally analytic set is a subset X in Cn, such that for each P in X, there is an open subset W with P in W, which is an open subset in Cn, and finitely many holomorphic functions, F1 to Fs, such that the intersection of X with this W is the zero set of all these germs. And if I consider U an open subset of Cn, then a subset of U is called an analytic subset if X is locally analytic and closed in U. I have an example. No, I don't. Not yet. Given holomorphic functions F1 until Fs from W to C with W open, I will denote by V of F1 to Fs the zero set of all the germs, of all the functions. Now I have examples. For instance, then Cn is equal to V of the zero, and Vasil, empty set, with the V of 1 are analytic subsets of Cn. And also, if we consider a sequence of non-zero points in C, which converge to a point, to the origin in the case, if X is the set of all these points, then this is not locally analytic, because the function which is 0 here has to be the 0 function. Well, this was an analytic set. When I want to work locally, it's good to work with germs of set. I will define it here. Given a topological space X and a point small x there, I say that two subsets A and B of capital X, such that my small x is in both of the subsets, are equivalent if there exists an open neighborhood U of small x, such that the intersection of A with U is equal to the intersection of B with U. And I call the equivalence classes by this relation germ of set. This is the germ of A at P, and I denote it this way. I have three definitions to give. The first one is when a germ is contained in the other. I say that AX is a subgerm of BX if there exists a representative A of AX and one B of BX, such that the representative of A is a subset of the representative of B. And also, the intersection of germs is nothing more than the germ of the intersection of representatives. I mean, I choose two representatives, A of A and B of B, and I take the intersection of both and the germ there. And the same with the union. So the germ AX union to the germ BX is equal to the germ of A union with B at X for a representative A of AX and B of BX. A lot of definitions. Then a germ of complex space is nothing more than a a germ at X of a local analytic subset of Cn, and together with the local algebra on X quotient with I, where I is the ideal which defines the germ. For instance, if f is a function in ON X, we consider an open neighborhood U of X on which f converges. The hypersurface defined by f is the germ v of f at X, which is the germ of the subset of the zero set of f. Okay? Together with the ideal ONX with the ideal generated by f. So again, given an ideal in ONX, it defines a germ of complex space as the germ of the zero set of this ideal. It means the intersection of the hypersurfaces V of Fi at X. And given a germ of complex space, I can look to the ideal of it. It's the ideal of the function germs on ON, which such that the germ X is a subset of the hypersurface defined by F. Well, then, given an ideal, I can look to a complex space, and given a complex space, I can look to its ideal. It's not very hard to see that this inclusion is true. An ideal is always a subset of the ideal of the, we say variety, of the variety of it. But the equality is not true. The other inclusion is not true. However, there is a very important result. It's called the Nullstellensatz theorem, which assures that this equality is true. The ideal of the variety of the ideal is equal to the radical of the ideal. Okay? Well, now a germ of analytic space is nothing else, nothing more than a germ of complex space defined by a radical ideal. That is, the local algebra, ON quotient I, is reduced, where E is the ideal which defines the X. For instance, if I consider the ideal I generated by X squared in O1, then V of I0 is the point 0. It is in this case, it defines a germ of complex space with local algebra, this one. Okay? This is not an analytic space because the local algebra, you can see if I write here, no? It's ON quotient X squared. You have that X is not 0 there, but X squared there is equal to 0. Then X is a nilpotent element. So this is not reduced. So it's a complex space, but not an analytic space. And given a complex space, I say that it is irreducible if always that it can be written as a union of complex spaces. Here I said x1 and x2. Then one of them is equal to the whole space. Here, I have a lot of results in just one slide. I put in a table, how do I say, a resumo? Sorry? A summary, thank you. A summary of how these things relate. So, as I said, given an ideal in ONX, I can always look to the variety of it. And given an analytic space, I can always look to the ideal which define the ideal of it, the set of the functions that are 0 there. So I have this relationship here. What I know is that this ideal is always a radical ideal. And if I have two ideals, that I is a subset of J, then the varieties, they reverse the inclusion. Then V of I contains V of J. And also, if I have two analytic space, V as a subset of W, when I do the ideal of them, the inclusion is reversed again. If I take the addition of two ideals, it's the same there on the other side to take the intersection of the analytic spaces. If I take the product, it's the same as taking the union of analytic space, but if I take the union of analytic space, I have to take the radical of the product on the other side. Also, with the intersection, then if I take the variety of two intersection, is the union of the variety of the varieties. And if I take a union of analytic space, again, is the radical of the product of the, sorry, I lost myself. Here, if I take the union, I have to take the intersection here. An ideal is prime, if and only if the analytic space defined by it is reducible. And I can take the minimal decomposition. When I take an ideal and decompose it as prime ideals, then the variety is decomposed as a union of analytic varieties. And also, if I take already here the decomposition, then it's intersection. Okay, this was it about the complex space and analytic space. I hope that's clear. And now let's go with the local algebra of a germ of analytic space. If I take X, P, and YQ, two germs of topological spaces, I will define which a germ of continuous map here. It's given by an equivalence class again. So a continuous map, a germ of continuous map from XP to YQ is the equivalence class of continuous maps F from U to W, with F of P is equal to Q, where U is a representative of XP, W is a representative of YQ. And which equivalence class? The equivalence class by this relationship. I say that two such germs, two such maps, F1 from Y1 to W and F2 from Y2 to W, are equivalent if they agree on an open neighborhood of P which is contained in the intersection. Well, this was germ of a continuous map, and the germ of an analytic map, if I consider analytic spaces, germs of analytic space, then a germ of map is a germ of an analytic map if some representative is the restriction to X of an analytic function on an open neighborhood of my point. When Y is equal to C, instead of say germ of an analytic map, I say germ of an analytic function. Then I denote by OXX the algebra of germ of analytic functions from X to C. It's a local algebra whose maximal ideal is equal to the germ of analytic functions, which takes my pointing at the germ, my X to 0. It's called the local algebra of my germ. As I said before, if I consider a germ of analytic space X and Y the ideal of it, then the local algebra of X is equal to this quotient. And also, my X is a germ of a submanifold. If it's a germ of a submanifold, then the local algebra of it is isomorphic to OK, for some K. And if I consider a germ of analytic map phi from XX to YY, then the composition with phi induces a map of k-algebras, which I called phi star, which takes a function germ f on y to the function germ f composed with phi from x to c. Okay, thank you. And I say that two germs of analytic space x and y are isomorphic if there exists an analytic map phi from x to y with a two-sided inverse, which is an analytic map too. Our goal here is to conclude that two germs of analytic space are isomorphic if and only if their local algebra are isomorphic. And for this, we have this theorem on the way. If I take X, a germ of analytic space in Cn, and Y, a germ of analytic space in Cm, and if alpha from the local algebra of Y to the local algebra of X is a C-algebra homomorphism, then there exists a unique germ of analytic map phi from X to Y such that the phi star, by the composition that I defined before, is equal to alpha. And the first result, two germs of analytic space are isomorphic if and only if their local algebra is isomorphic. And to see this with the theorem before is not hard. By Nunes Telanjas, there is a one-to-one correspondence between reduced analytic algebras and germs of analytic space. And by the previous theorem, the isomorphism class of reduced analytic algebras correspond to the class of germs of analytic space. It's a good point to stop now, Raimund. Should I go 2 more minutes? Yeah. Okay, I will just define the dimension. Given a complex space X, and all X its local ring, I will denote the maximal ideal always by M. Then the crude dimension of X, which is the dimension of X, is the crude dimension of its local ring. If you don't know it's the crude dimension of your local ring, it's the maximal length, K, of chains of prime ideals like this. P0, prime ideal is a subset, but not equal to P1, and then to Pk. So the maximal length is the crude dimension. By taking zero sets, the crude dimension is the supreme of the length of the chains of irreducible subvarieties like this. I have an example here. For the Cn, when x is Cn, for all x equal to n, I consider this chain of prime ideals, the zero ideal, the ideal generated by x1, the ideal generated by x1, x2, and so on, go on. It follows that the crude dimension of Cn is at least equal to n. And it's not trivial to see that's equal n. We always do this using computation methods. I think we will learn a new one this week, no? And my theorem, if X is a germ of complex space with this irreducible decomposition, then the dimension of X is the maximum of the dimensions of the germs which appear in the decomposition. And now I can stop for the interval.
We have a 5-minute break, but before that, let me just tell you some important announcements. So this is the Wi-Fi link if you want to use, okay? And also you can use the blue one. The tool is everywhere here, inside the building of something. And what else? So a very important announcement, of course. So we are planning to have a happy hour next Wednesday. It will be if you want to join us, you are requested to pay 50 Brazilian reais. Okay? It includes the meal, the rent of the fireplace, and also maybe the transportation from here to the fireplace. Okay? So please join us. I think it will be very fun for all of you. And now 5 minutes break. Okay, Pauline, you want to say something?
No.
Okay, 5 minutes break, please.
Vai ter break agora, uma pausa. 5 minutes.
Tudo certinho. Ah, mas nervoso. Should I go? Posso ir, será? Já pode ir, será? Já posso começar? Já posso começar? Acho que sim.
Eu acho que pode começar.
So let's continue. We just saw the definition of analytic map germ, and I put a slide here to call our attention that we can say the image of a map germ. And why is that? For instance, if I consider the map germ, which is represented by the map F from R2 to R2, which takes xy to x times y. Then I can choose how small I want representatives in the source, such that the representative in the target don't have the same germ. Here I put a square with side 2r's centered in the origin. So it's a representative of the R2 in the source. And the image of this square by F is this little tie here. Here you have the line V equals to RU. And here you have the line V equals to minus RU. Okay? And then I'm seeing myself here, Paulinho. I'm seeing myself. And here I took the open set limit bounded by the lines y equals to x plus r, and the line y, this is not good, y equals to x minus r. So it's another representative of R2, and the image of descent by my map F is equal to this almost a tiny little crooked, and it's bounded by two parabolas here. So it doesn't matter how small I take a ball here in the target, I get different sets here and here. Here is like lines, and here is curve. So it's not the same germ. This is why I can't say the image of the germ. But sometimes I can. And this is when, if I consider a map F from X to Y between topological spaces, I say that it is closed if the image of a closed subset is a closed subset. I say that it's quasi-finite if for our P in the target, the fiber F minus 1 of P is just a finite number of points. And I say that my map is finite if it's both closed and quasi-finite. And in map germs, if I consider XP and YK two germs of topological space, a germ of continuous map from XP to IQ is called finite if it has a finite representative. So for instance, my germ from the example, which was the problem, is this one. And this is not finite because the inverse image of the 0 is equal to a line. Well, then I have this lemma, which will solve my problem. If f from x to I is a closed map between topological space, I take P, a point in X, and I call f of P of Q. Then I assume that f minus 1 of Q is just the point P. In this situation, if A and B are subsets of X with P in the intersection, such that the germ of A in P is equal to the germ of B in P, then the germ of the images are the same. And if I'm working with a map germ, with a finite map germ, I can always assume this here for the representative, because, you know, f minus 1 of Q by hypothesis is just a finite number of points. So I take smaller representatives for it to be just 1 point. And then in this situation, I can define. So if f from xp to yq is a finite germ of continuous map, the image of f is equal to this germ here, represented by f of x, where f from x to I is a finite representative with that hypothesis. And when I can say the image, now when the germ is finite, it's called surjective if the image is equal to the germ at the target. Then, when I'm working with finite maps, I have some good properties. This is the Remert's property mapping theorem. The image of any finite analytic map germ is analytic and with the same dimension. And also, I want to define the degree of a finite map germ. The degree will be the number of points in the inverse image of a point. Then I have to say that it's independent. And this is the theorem. If f from x to I put the 0 here to be able to write the theorem, is a finite and surjective analytic map germ with y, the target, are reducible. Then there exists a hypersurface D in y such that for all small enough representative y and D, the fiber f minus 1 of I has constant cardinality for all y in D. Okay? So this shows that the cardinality of the inverse image of a point, it's almost all the same. And this number, this cardinality, is what I call the degree of the map. And there is a nice way to calculate it when the target has a special property with Cohen-Macaulay. So if f from x to cd is a finite surjective map germ, if she's is Cohen-Macaulay with dimension d, be patient, Cohen-Macaulay will appear in a minute. Then the degree of f is equal to this dimension here, okay? Where this f1, fd are the coordinate functions of f. Okay, this was finite map germs. Now I'm going with the singular locus and the Jacobian criterion. So first, let's define the singular locus. So a germ of complex space XX is smooth, or I can say that X is a regular point of X if the germ is isomorphic to CD. This is a complex space germ for some D. I mean, the rings are isomorphic. Otherwise, I say that the germ is singular. If X is smooth and then OX is isomorphic to OD for some D, then this D has to be the dimension of my germ. And also, if I fix a representative of X, I consider sigma the set of points X in X such that X is not regular at this axis. Then the singular locus of X is the germ of the sigma. Okay? And I have how to calculate here. It's the Jacobian criterion. Here I put more simplified the way you use, but we have the notes for the course, and there is the Jacobian criterion, like the theorem that it appears. I would need more definitions to put it here, so this is why I didn't put it. If I consider X analytic subset on an open subset U of Cn, defined as the zero set of these maps here, F1 to Fs. And if for all X in my X, the dimension of the germ XX is equal to n minus C. Then the singular locus of X is an analytic set defined in this way. It's equal to V, the variety, the zero set of the ideal generated by the coordinate functions of F plus the minors of size, codimension of my germ of the Jacobian matrix of the map. Okay, I put an example. For instance, if I consider X in C4, the germ defined by these functions here. Then I made the calculus in singular, the dimension of X is equal to 2, and therefore the singular locus is equal to the zero set of the ideal, which defines my germ, plus E. Here is the 4 minus 2, is 2 again. The minors of size 2 then of the Jacobian matrix of this map here. I just put here the Jacobian matrix. It gives me a ideal generated by a lot of things. Singular simplified it for me. And here, the zero set of these functions here is just 0. Okay? Now, finally, you are ready to define the complete intersections. So let X be a complex space defined by an ideal Y. I mean, X is equal to V of Y. I just putting at 0. Let K the minimal number of generators of Y. I say that X is a complete intersection if the dimension of X is equal to n minus K, or if the codimension of X is equal to K. For instance, as Roberta said, for hypersurfaces, from the first part of the course, if X is F minus 1 of 0, F from Cn to C, the dimension of X is equal to n minus 1, then X is a complete intersection. And another example, if I consider X, the germ defined by XY, XZ, and YZ. This is the union of the 3X in C3. It's dimension 1. And the minimal number of generators of this ideal here is equal to 3. Therefore, it's not a complete intersection. Okay? Although I have to do some merchandising here. It is not a complete intersection, but it is a determinantal variety, which is the issue of the course of next week. Because this germ is given as the zero set of the minors of size 2 of this matrix. And it has the expected codimension that is going to be defined there. Okay? Well, Cohen-Macaulay, I promise. Cohen-Macaulay models. I have here the definition. I consider a local ring, R, with a maximal ideal M, and N, capital M, an R model. I say that sequence, F1, F2, Fr, of elements in the maximal ideal is a regular sequence of the model if F1 is not a zero divisor of M. And for each E, for each I, Fy is not a zero divisor of this quotient here. Then the depth of M is the maximal length of a regular sequence like that. Over a Noetherian local ring, it's always true that the depth, I'm saying this right, depth, yeah, is less than or equal to the dimension of M. And when the equality holds, we say that the model M is Cohen-Macaulay. And a ring, a local ring is called Cohen-Macaulay if it's Cohen-Macaulay as an R model. And a complex space is Cohen-Macaulay if its local ring is Cohen-Macaulay. And this is to say that a complete intersection is always Cohen-Macaulay. This will be useful for the other lectures. And now the definition of ICES. What is an ICES? An ICES is an abbreviation for isolated complete intersection singularity, which is a complete intersection with isolated singularity. I mean, the singular locus is just zero. For instance, I took here the complex space defined by these two maps here. It's a complex space in C3. The dimension of it is equal to 1. The singular locus of it by the Jacobian criterion is equal to the variety of the ideal that defines it plus the minors of size codimension of my germ, which is 2, of the Jacobian matrix. So here are the partial derivatives of the first function, the partial derivatives of the second one. I just make the calculus here. We can see that the zero set of this ideal is just 0. And then this is an example of an ICES. Another important property of an ICES is that it's a reduced germ. What's a reduced germ is the local ring is reduced. It means it has no nilpotent elements. And I can show that a germ is reduced by the Serres condition. So a germ of complex spaces is reduced if and only if it satisfies those two Serres conditions. R0 is that the singular set of the germ has codimension greater than or equal to 1. And S1 is that the depth of OXP is greater than or equal to the max between the height of P and 1 for all prime ideals P no X. And I mean, it's true if X is Cohen-Macaulay. It's what we need. An ICES is Cohen-Macaulay, okay? And if I assume that the ICES has dimension greater than or equal to 1, as the singular locus has dimension 0, its codimension is more than or equal to 1. Then an ICES with dimension greater than or equal to 1, it's always reduced. Okay? And do I have some more time now? Yeah? Now we will define the K group. It's going to be clear on the other lecture is the relationship between the K group and the ices, the versal deformations of the ices and the K group. So let's see it for a while. Now, I will assume that K is the field R or the field C. The contact group K is the set of pairs of germs of diffeomorphism, small h and capital H, in this way, a small h from Kn to Kn, and capital H from Kn times Kp to Kn times Kp, such that if I compose the capital H with the projection on the first coordinate, I get H, first coordinates, né? I get H, and the projection with the second coordinate, the composition with the projection on the second coordinate is equal to 0. Okay? That is, capital H of xy is equal to small h of x, capital H2 of xy, where this is equal to 0. So this is the K group. The set of pairs here this set is the K group. If I consider just that when the small h is the identity, it is a subgroup, which I usually denoted by C. Well, if I consider two germs F and G in Mn, O, and P, I say that they are contact equivalent, and I write in this way. If there is an element of the K group, small h, capital H, such that the capital H of x of fx is equal to this. I mean, the graphic of F is taken to the graphic of G. Okay? If it's the case, then the diffeomorphism capital H sends the graph of F into graph of G, leaving Kn times 0 invariant. And also, we will need to define the tangent space. At the notes, there is an exercise which motivates it, the definition. The tangent space and the extended tangent space of K equivalences are Tk of F is equal to Tf of Mn theta n plus F star Mp theta F, and the extended tangent space, I just take off this M here. Tf of theta n plus F star Mp theta F. I have an example on the next slide. And also, we define the K codimension of F as the dimension of Mn theta F for the tangent space, and the Ke codimension as the dimension as a K vector space of theta F over the extended tangent space. This number here is also known as the Turina number and denoted by tau df. It's related to the number of parameters I need to a versal deformation. Versal, you are going to see deformation of F. For instance, I consider this map here, F of x1, x2, x1 square, x2 square. Then the extended tangent space is the O2 model generated by the partial derivatives of the first map, 2x1, 0, the partial derivatives of the second map, 0, 2x2, okay? Plus the second part, that's F star, theta F, né? So the ideal generated by x1 square, x2 square, theta F. Then the codimension, I have to see what's missing there, né? What's missing there is this 1, 0, 0, 1, x2, 0, 0, x2. So this dimension here is equal to 1, 2, 3, 4. So the Turinian number here is 4. Okay? And we are close to the main result. The following statements are equivalent. Two map germs are co-equivalent, and there exists a germ of diffeomorphism, H from Kn to Kn, such that H star of F MP is equal to G star MP. And this leads to this. So given a map germ F from Kn to Kp, the local algebra of it is equal to On quotient F star F of MP On. Okay? And we can show that if F and G are map germs with finite K codimension, then F is co-equivalent to G if and only if the local algebra are isomorphic. And in the complex case, we can take this hypothesis here. I do not need the finite codimension. And to finish, I have an example. If I have capital F from Kn to Kp, a germ of rank R, then up to a equivalence, we can take F in this form here. It's X, F of xy, where X is in Kr and Y is in K and minus Y, with the small f here in the square of the maximal. Okay? If I take F0 to be the map F0 of Y equal to this F of 0Y, then the local algebra of capital F is equal to the local algebra of F0. Then if the K codimension of 0 is less than infinity, and the local algebras are isomorphic, it follows that F is co-equivalent to this trivial unfolding here of F0. Okay, and this is it. I need to say that there is notes for this course. They are going to be at the site in some point during the week. And thank you very much.
What's the operation about the K group? How was it defined? Because it was kind of fast and I couldn't see it.
The definition of the K group, if I understand well.
Yeah.
It's here. Maybe it was too fast.
Yeah, it was kind of very fast.
Here, it's the contact group. So I considered the group of the pairs of germ of diffeomorphism, small h and capital H. Here, H from Kn to Kn, and capital H from Kn times Kp to Kn times Kp, such that capital H relates to small h in this way. The first coordinate is the small h, and the second coordinate depends on the two variables, but it takes, when y is 0, it's equal to 0.
And what is the operation in this? It's a group. How do you, is the composition, what is it?
It's the composition. It's the composition.
So compositions of a pair, so you have a small h and capital H?
Yeah, small h1 and capital H1.
Yeah.
And small h2, capital H2, and do the composition.
And then you compose each component.
Yeah, and it's more, what's more beautiful is this relationship, né? That two germs are co-equivalent if there is a a diffeomorphism which takes the graph of one into the graph of the other.
Okay, and then
Because of
you have
this.
some invariant that was also defined on this, the invariant, the number that you defined later.
It's the Turing number
Yeah, well,
here. Then I have the kind of the tangent space to the orbit of a map F. Okay, and the Turing number is the dimension of the modulus of along F to this tangent space.
you have a theta f and a theta sub f. What is the difference?
I mean, they're the same, sorry.
Oh.
They're the same, sorry.
Oh, okay.
Okay,
Okay. Okay, thank you.
thank you.
Okay, thank you very much. Okay, let's thank the speaker again.
Okay, I can.
Pauline. Tem convite.
Yes, but I'm also moving sometimes.
Okay.
point. That's the official title.
Okay, now let's start one of the follow-up course. It is the F2, Munich vibrations, non-isolated singularity, and the polar degree of projective half-surface. The lecturer is Dick Sisma. Please go ahead.
Yes. Thank you very much for giving me the opportunity to talk here. In fact, the first part of this talk is the talk that should be given by Mihai Tibar. But as you know, he's not here, and he asked me to replace him, and I will do so. And in fact, I will mix part of his talk with the talk I have in the second part of myself. So there will be a mixture of those two. In fact, we prepared both things together. So what is follow-up course? So follow-up course means that it was a course last year over internet, and this is the same subject. And so when I prepared the course, I thought, okay, did I remember by myself what I talked about last time? And then I found that I had to look at my notes. So I started to do it from the beginning. And in fact, I will also give this lecture from the beginning, perhaps skip some extra details, but try to get in the beginning as elementary as possible. So if all of you, was one of you who looked at the course, recorded course last year? Okay, nobody. Okay, that's fine. Then we start just from the beginning. If you want to look to the notes of last year, you find them on course B, and even the recordings you find. No, you can't find the recordings not immediately, but anyhow, the sheets of that year you find in course B, and most of the sheets are copied also today. Okay, let's just start with the beginning of Mihai's talk, which is taken from my notes, since it was also the beginning of my talk. So this is the overview, and since this is about singularities, and singularities they have to do also with pictures and with topology and geometry. You already saw this morning that it has also to do with algebra. And if you mix all these ingredients together, you get a very nice field. Okay, just in the first picture, well, where is it? Where it is here? You see no singularities. But here you have a special point, and so we call that a singularity. Here you see a special line, so here you have a one-dimensional singularity. Also here, the famous Whitney umbrella. You see here a line, and a line where the space is not smooth. And also here below, over the reals, it looks smooth, but in the complex sense, it's not smooth. It has also not dimension 2. Here you find also a singular line, and in the transversal direction, you see that there is a cusp. This is going up first here and going down over there. So it's not a trivial family of cusps, but it's a family what is something going to happen. And then here you have 3 planes, a kind of arrangement of planes. The easiest one, given by the equation x, y, z is equal to 0. And what you see is smooth parts, the 3 planes, but not the coordinate axis and the center. So in fact, this is a stratified, you can stratify this space also in smooth pieces, and stratifications will play an important role. Okay, there are some names attached to singularities, and they are mentioned here. So you have especially to remember the Whitney umbrella, which is called D infinity, and the A1 singularity, which is the usual Morse singularity. Okay, just another picture. I already, for the beginning, I already showed you certain things in Surfer. And what you see here is the so-called Roman-Steiner surface. And in the middle, you see the situation of the triple point. But anyhow, the 3 planes are over here. But at the end, somewhere here, here, and there, you see Whitney umbrellas. And of course, you can count the number. So there is 1 triple point. And then on each of the axes, you have a Whitney umbrella here and a Whitney umbrella at the other side. And altogether 6. And they enclose kind of bubbles. How many bubbles do they enclose? There are 8 possible directions, 50%, 4 bubbles. Okay, so if you take the function defining this Roman-Steiner surface, it will have 4 isolated critical points inside the bubbles. Okay, that's enough. Another picture of it. And there you just is explained what is what. And here you find a reference, and in the I expect that in the slides of that year you can click and get to the publications. Okay, now let's start with the elementary construction, the construction of Milnor. So we just begin with a holomorphic function germ, and we are going to define the so-called Milnor vibration. Okay, this the top space here is inside Cn plus 1. Then this circle is the kind of is meant to be a sphere of small radius. Then this is the target space. So this here is the origin. Here's a small circle. Here is a small value t, a generic value. And then if you look to the fiber over 0, you find a singular variety. Here it looks that it is isolated, but as we have seen in the examples before, it can also be non-isolated. But as soon as you go a little bit to the right, or away from the origin, you get something smooth. Since these singular values, they are isolated in complex holomorphic function theory. Okay, so this means that that if you take a small neighborhood, then you get a set of smooth fibers except in the center. And they constitute a so-called fiber bundle. Of course, you have to prove something, transversality and that kind of things. But I refer to the literature to look to all the details. But the feeling is very important. So this is the most important picture of the lecture. We follow much more pictures. And so this tube around the singular fiber is called the Milnor tube or the Milnor neighborhood. And the Milnor fiber is just this thing over there. And then the very straight things which I'm going to prove is that this topological type of this manifold is very special in the case of isolated singularity. So the word isolated singularity does not appear in the slide, but it appears here upstairs. Don't forget. In the isolated singularity, this Milnor fiber has a very special homotopy type. It's just you take a set of balloons, a set of spheres, and you put them together in one point. And the dimension of the sphere is just the real dimension, is half of the real dimension of the Milnor fiber. The Milnor fiber is n complex dimensional, 2n real dimensional, and this is half the dimension. Okay, so And then the important other thing is that if you walk around this circle, then you go from the Milnor fiber into itself. So at the end, you get a map from your Milnor fiber to itself in some way. And in the isolated singularity case, so this is in the hypersurface case, this map is never the identity unless you had no singularity. Okay, then the most important singularity, no, not important. Why? Oh, okay, important, is the Morse point. It's given by z 0 squared up to zn squared. And then the Milnor fiber is this equal to delta or equal to t. And if you take delta real, then this is the equation of a sphere of radius square root of delta if you also take the variables real. But if you allow also the complex values, then you have this upper thing. Then you see this is a subset, which is a real sphere of dimension 2. And it turns out that the Milnor fiber is just a disk bundle around this sphere. So it's also something to compute. So you don't see this by head, but you have to do something. And this means that the Milnor fiber has the homotopy type of an n-sphere. That means that if you plug in one n plus 1 cell, which is not there, but you plug in, then you get some contractible thing. Yeah. And now we are going to prove Milnor's bouquet theorem in the isolated singularity case. And so what we are going to do is the system that Mihai also did in more complicated cases, and we will talk about that soon. This is the picture we had. This is a familiar picture. Now I take a deformation. So I deform the critical point. So by adding a generic linear function, what happens? The single critical point splits into a set of other critical points. And if I do this in a clever way, with a generic way, then all these points, they are Morse critical points, which I have studied the slide before. And if the deformation is small, I can look, then I can, there is here a vibration outside. Here is also still a vibration, and I can take care that the two vibrations are equivalent. So if the Milnor vibration over the circle here is equivalent to the Milnor vibration over the circle there. Here there are more points where where it's not a vibration, the values of the critical points. Okay, now the idea is as follows. We take the Milnor fiber, but we take relative to the tube. So it's good to work with the so-called vanishing homology. You take the Milnor fiber inside the surrounding space. We call that vanishing homology. Now, what I'm going to do is look to this picture. This picture is here, where I just fill in what you see here, the number of disks completely. So there is a homotopy equivalence between the full disk and this symbol. This is a kind of sense, a sense of how do you want to call it? But there's also a homotopy equivalent between the point and these set of 3 sticks. The important thing is that I can do deformation retraction from not only downstairs but also upstairs. In that fact, this full tube is then going back to the thing which is above this. So this includes still the critical points. This is only possible if this, where I'm just deforming, there are no critical points. And then I take one point and I move to the others. This is also required. Now the first has become smaller, the E has become smaller, the F has become bigger. And now, due to homology, I can cut out the common part, so to say. I cut out the open stick. So where I left is things above the 3, in this case the 3 discs, modulo the fiber, not this fiber, but a boundary point fiber. So it looks like I have the Milnor vibrations of these local singularities, but in fact these tubes are too big. So I cut out also the things outside the neighborhood of this. Since there the two spaces, the F and the E part, they are homotopy. There's no singularity, so it's a product. So I have left over here, the cutting out is done here, with the direct sum of Milnor, of relative, of the vanishing homology. And if there are more points, then the number of, then the homology is concentrated in the dimension, the top dimension, so to say, and each critical point counts for 1. So here has, in that case, you have one number, the number of points, and this number of points is called the Milnor number. So this is a very fundamental construction which will come back all the time. So repeat. Okay, so first deform this critical point. Infinitely many critical points. Then you have finitely many singular fibers. There are finitely many tubes around singular fibers. Then by deformation, retraction, and excision, I can come to the big tubes above these things, which is over here, and then I cut away the things far away from the critical point, and I have the direct sum of the homology. Okay, this is the Bouquet theorem stated in homology. So if I have a bouquet of spheres, homotopically, then the homology behaves in this way. Okay, any questions? Yeah, so what I just do is taking the function plus a generic linear form. And that's all. How I choose? Generic. Oh, just what you want. So it's okay, there is of course a Zariski set which you can define. And you have to get outside this Zariski set. So it's a kind of tangency property. Yeah, so it's, but I just, I'm more a topologist. I think about Char's theorem and then it's fine. But of course, the set is well defined, but I'm not going to define it over now. Okay, the next step is to go to non-isolated singularity, but now I change the set of sheets and go to the set of sheets which I made because I had to replace Mihai. In a certain sense, what was here was also just in his, oh, it comes, Diervoorstelling. This is Dutch, if you. Okay, Mihai had made some notes, and these notes are available on this website. And then in big details, you can see what I'm going to tell now to you in a schematic way. And but there are still many technical things to say, also in theorems, and I will be a little bit sloppy. But I want really to give you the ideas about this. Okay. Okay, now we are going to Bouquet theorem. But now the difference with the earlier picture is that the space itself is not smooth. So here you see a kind of surface where I have a singularity on the surface itself already, which is transversal type of cusp. So in the picture, the space X itself is two-dimensional, but it could be any dimensional, and in general, any type of analytic space. Mostly we take irreducible and equal dimensional, but you can try to do this came with in many situations. Then there is a stratification of the space. Stratification means a partition in smooth pieces. And it's a Whitney stratification. And so this means that there are some technical conditions to be satisfied. And you can read that in the literature, which exactly. And then you do exactly the same construction. So the sigma is the name of this singular set. It includes the origin here. And you get in a stratified set, again, the Milnor vibration. And since this construction was made by Lei Dongzhang, it's called the Lei-Milnor vibration. And the Milnor fiber is called, the Lei-Milnor fiber is denoted by Fg. So in this case, it's only stratified smooth. So it's not smooth in general. If you go to the example, in the three coordinate planes, and if you take just a linear function, which is x plus y plus z is constant, so it cuts, and then you see that it cuts the space in three lines, which have itself also singularity. So the Milnor fiber is no longer smooth. That's the remark. It could be smooth, but it's not necessarily smooth. Then there is a very special case. This is the complex link. And this complex link is you take a generic linear function. And of course, you will ask again, what is generic? And I will give you the same answer. And this complex link is a fundamental concept in this theory. It replaces certain things about the relink. And a fact is that if X is a complete intersection, then that complex link itself is a function with L is then a function with isolated singularity with respect to the stratification, is a bouquet of spheres. I will talk about that later in this talk. But in general, the complex link is not concentrated to homology in the middle dimension. It can have much more contributions, and so we could perhaps discuss some examples in the exercise session. What I also need is the topological concept of suspension. Okay, so the suspension is of a topological space. You take 2 points, one in the north and one in the south, in your mind, and you take the connections between each of the 2 points with the space. So if you do this for the circle, you get the 2-sphere, and if you take this for S1, wedge S1, you get something which is not immediately the wedge of the 2-sphere, but homotopy equivalent to a wedge of 2 spheres. More general, you get the suspension of n-1 sphere is an n-sphere, and the suspension of a wedge is the wedge of the suspensions. There's a general fact. If you add some extra variable like w squared to G, so then the space becomes, starting space becomes 1 dimension higher, but it's only quadratic, then the new Milnor fiber is the suspension of the old Milnor fiber. This is a version of the so-called Tom Sebastiani statement. And if you do this several times, then you get the k-fold suspension of the Milnor fiber, so the F is not there, of G. Okay, so suspensions play an important role. Then some other concept is the normal slice, which is just rather easy concept. If you have a singular stratum, like over here, this I have to go back. Yes, if you have a singular stratum, then you take just a transversal in the complementary dimension of the surrounding space, and you intersect with X. Then you have the space X intersected N, which is again an analytic variety, and its complex link we call the complex link of the stratum. And due to the properties of the stratification, so these Whitney properties, other properties, it does not depend on the point of the stratum and on the way you slice. Of course, this is all technical, and you have to look in to the details if you really want to have the full proof. Okay, now what Mihai showed. We start with a function g on this analytic space with isolated stratified singularity. Of course, you have to define what this is. In fact, this is, you want to have that on every stratum, the restriction of the function has an isolated singularity. Okay, and then you have also sometimes a zero-dimensional stratum, and this is automatic singularity, called a singularity. And then Mihai proved that the Milnor fiber is again a bouquet of something. What is that something? Now, you take the complex links of every stratum. Now, so it was just defined before in the page before, the complex link of the stratum. Okay. And you take the suspension as often as the codimension of the stratum is, to get the, so to say, the full dimension. And you do this for every critical point. So you take this for all the strata, and then on each strata you have a number of critical points. So you do this for every critical point. And that's the statement. So I proved this statement before in a very special situation, that the space has itself had an isolated singularity. And then the statement was quite easy. I had the complex link of the zero-dimensional Z, and then I had one other stratum, which was the smooth stratum, and in that case, this suspension of the complex link were just spheres of middle dimension. Okay, so the case of a hypersurface was showed by Ley. The smooth case was showed by Milnor, and I recall the proof. This was a Briscoe type of proof in the beginning, and then Ham showed this for isolated complete intersections. And in fact, there are two proofs in homology and one in homotopy. And this was the proof in homotopy, and I will say a few words about that. But first, the proof which is about morphification, which is only homology. So the story is exactly the same as before. Now you take a morphification, just take a generic linear function. And now it has to satisfy even more conditions, since it has to be generic for every stratum, etc. And then you get on every stratum the finite number of singularities. Also, you have a could have a singularity at the origin, and then you can also expect generic singularities in the stratified sense. Okay, this, as an effect, we get generic critical points on each stratum. So if you look near to the origin, then the effect of adding a linear term here is that the function is equivalent to a linear function. So what you get is the intersection with a linear function, so you get a complex link over here. So there is one contribution, which is the complex link of this point. If you get into a stratum, then you get a complex link of the transversal singularity, but since it has critical also in the smooth direction, you have to add variables in the other direction, and in the generic case, you have just to add a coordinate to squared, which means that you will get something like this over here. Thus locally, we get the Milnor fiber of certain suspensions of the complex links of the stratum. Okay, from the other beginning of the lecture, I have exactly the same proof. That's why I repeated that proof for you. Is nothing changes, only there are more technicalities, since there are more strata, so you have to have stratified maps and all these kind of things. And what I explained to you, that each local fiber is now of this type. The complex links of the stratum, and this gives you in homology the wedge composition. And so this is the proof of the wedge theorem in homology. And I always tell you that on the top dimensional stratum, you had just the Sn minus 1. But the main question is, how many of each type? So we also want to so you don't really have a Milnor number. So you have, for every kind of complex link, you have some other kind of building block. And this was not answered in this way. So what we need, Terry, is to have a counting, and perhaps an algebraic counting of this number of points. And I think this is possible, but Mihai solved this in some other way. Okay, so I have still some time before the break. Okay, so let's relax a little bit. Since before using the other method, we have to talk about polar methods. What is this? Again, a generic linear function, or just a non-generic linear function. You can also start with any linear function and move to generic as soon this is you like it, or that it is necessary. So then if you have two functions, G and L, then you have a map to C2. That's just like you in certain cases of complete intersections. And then we are first going to look at the picture. We want to have look for the critical points of this map. So when is this map critical? So if the gradient of G and the gradient of L have the same direction. Or you can say, write down a matrix. Anyhow, if X is smooth, then this is much easier than in the other case. And also you have to do this stratified if the space X is not smooth. So I do here more or less that the space X is smooth, but if the space X is not smooth, then you have to do this for every stratum. And this defined, so you define the set of critical points, and you have to take the critical set, but you take out the zero set of G, the zero fiber, and take complete. Usually the space gamma can have any dimension. But there is a kind of polar curve lemma that if you, in the generic situation, you have always a curve or a void set. There can also be no polar. Okay, and of course there's also vibration, or not stilly vibration, it's a map to C2. Oh, going back. There's also map to C2. And the image of the critical set is called the discriminant, which is over here. And the discriminant has also the name of Surf diagram. The Jean Surf. So this is all 40 years ago, I think, or even longer perhaps. He used this diagram and technique to prove several things about this. Okay, so you have, and in a certain sense, if you map this curve to that curve, it's also a finite map. So I wrote here multiple points, so that is a multiple covering. You also have to think about what happens if I fix the value t and let every L, allow every value of L. Now, then I have no conditions. So the inverse image of this line is just the Milnor fiber. And if I just also put L a certain value, I have the fiber of this map. So this is one dimension less of this, let's say, complete intersection. Okay, so what to remember? There is a kind of a box neighborhood here. And above this, we have a vibration. If you take out the discriminant, we have the fiber of the vibration. If G and L are both equal to 0, G is the, if L and C, T and C are both not equal to 0 and not on the discriminant. And what they said, the inverse image of this horizontal line is the original Milnor fiber. Okay, so this is this. This is. Okay, now we get a more difficult thing. Okay, Mihai showed that you get the Milnor fiber of the original thing from the Milnor fiber of this hyperplane section by adding certain cells. In the smooth case, you just add disks. So that was the case I explained to you. I had an n-sphere, so to say, and I had to plug in a disk there, a ball there. In the stratified setting, you have to plug in something else. These things are called the symbols of the stratified Morse singularities. Okay, and how many? Now go back. You have to plug in. The idea is that you have to plug in this number of intersections minus this number of intersections. Why is this the case? Already Leendung Trang knew this. In fact, the Milnor fiber, and I talk in the smooth case, since I know that better. In the smooth case, the Milnor fiber is a bouquet of this hyperplane section, is a bouquet of S minus 2 spheres. And you will like to end up with a bouquet of S minus 1 spheres by adding all these cells. That means that you have first to kill them. And how to kill them is that you just say, okay, these intersection points, they are really used to kill the fiber, the original homology. Since the inverse image of this space is contractible. And that means that if you move from here to here, and in this picture it looks that you get every point over there, but it's not true. Since this is complex geometry, there are multiple intersections. So you kill only one point of the multiple intersections. So you end up with this number of points minus this number of points. Okay, so this, you have to digest this, of course. So many. And then you are left with, after killing, you have to add the symbols which are related to the stratified singularities. And after killing the first, you end up with these things, which are just, again, the complex link of the strata. It's a little bit fast and a little bit sloppy, but the idea is that as soon as you put this symbol in it, then you get this singularity, this suspension of the complex link. And this is the number. Okay, now we have this number. Okay. And so this is the, and we have, that I did not say, that was a very good thing from Mihai's work at that time. You take, he could also prove that the attaching was trivial at the homotopy level. So that means that you need not only kill the homology, but also the homotopy. And so he ended up with a homotopy decomposition. And this is the number of building blocks. And there will be an exercise about that, the easy exercise in the exercise session. And but now we have two decompositions, one from one theory, one from the other theory. And they division in the same type of ingredients. Yeah. Now, the two compositions are the same, and that was proved by Mihai. And a naive way is to say, okay, if I have a decomposition with the same building blocks, same ingredients, okay, they must be the same. And that's not enough. So Mihai did some induction argument. And he wrote this down in these notes, which are background notes for this course. Then in the afternoon, I will have an exercise session, which here are the exercises already. So one thing will be about the complex link of this space, x, y, z is equal to 0, compute complex link. And then we do the same thing for G. This is a very easy function. Determine the Milnor fiber by the deformation principle, and we can do that together. And I promise you, it's useful and not too difficult. Okay, so what is the time now? Is this time for the break? Okay, then this is time for the break.
Okay. Any question? Okay, go ahead.
In the definition of the surf diagram,
Yes.
is it enough to assume that the linear form, well, of course, it's a linear form, so it defines a hyperplane. So is it enough to assume?
What I remember for the smooth case, anyhow, is that it's enough if it defines an isolated intersection, this intersection with isolated singularity. So if you have to go back to all these papers of Le Duong, and he wrote several, and during writing the paper, sometimes the conditions changed. So you have, especially in the monodromy theorem, where this construction was the geometry of monodromy is the title, which I just is very good paper to look for if you want to understand what is going to happen. I think what you said is enough.
Maybe another way to say it is to say that the hyperplane is transverse to all strata away from the origin, right?
It must be, no, it has to do with limits of tangent directions, I think.
You have to look at the limit.
Yes.
Yeah. Okay.
Any other question? Okay, let's have 5 minutes break.
Yes,
break.
5 minutes break.
Okay, let's thank the speaker. Sorry about that.
No, thank you for your, you're being quiet, a quiet audience. Okay, then in the meantime, I make this picture again. show you server. Oh. Yes. So going back to this case, the surrounding space is smooth. And in the isolated case, you had concentration of homology of the Milnor fiber in only one dimension. And this is no longer true in other dimensions. You can even see this already if you take just a hyperplane singularity and you make a product of it by putting this the same formula in one higher dimension with one less coordinate. But there is this Kato-Matsumoto result that is the singular set is S-dimensional. Then only in this range, we see here, you have can have non-vanishing homology groups. And if we specialize to the case that the singular set has dimension 1, which will be the rest of this lecture, then you have only 2 homology groups, which can be non-zero. Then you have the top one, which is for some reason always free. So it's also CW complex and cells in the highest dimension only, and there can be no boundaries, thus the homology must be free. And then you have homology in one dimension less, not always, can be 0, but it's not always free. It can also have torsion. And this torsion is not really so often studied, so to say. Now, what kind of picture we have now in mind? So the difference, so this picture is in the ambient space. And in the other lecture, the singular point was only 1 point, so it only one red point. But now the singular set is one-dimensional. So in the real picture, you have a number of real curves, but forget about real, we work in the complex world. So it's more or less two-dimensional real. So I try to make this in this way. So here you have only the 0 set, but then you have the singular set, which is part of the 0 fiber. And so I have pictured the 0 fiber here in a transversal slice. And nearby the 0 set, you have the Milnor fiber. So this is a piece of the Milnor fiber intersected with the transversal slice. In fact, it walks the Milnor fiber along every point over here, which is over this surface. In fact, since these are complex curves, the intersection with the Milnor ball are circles. So the two-dimensional real thing intersected with this Milnor, with this big ball will give a one-dimensional intersection. So, and you can walk now according to this, along this circle and come back. That's called monodromy. You can follow this. In fact, every circle vibration you can have in mind, you cut open the circle, then you have an interval, and that is trivial, so if the line to the other, and then you glue back and with a kind of map. And this is the monodromy map. And for each irreducible component of the singular set, you have this monodromy map, which we call vertical monodromy. And why vertical? Since in the first pictures we made, there was vertical monodromy. And we had also in the other pictures, the most fundamental picture, you had also the Milnor monodromy, which is mostly done, written as horizontal. You can also say I have a local system of transversal Milnor fibers. You can also call this the local system monodromy, or any name you like. Okay, so this is now. So this is for the original thing. Okay, so here are several definitions and conditions. The hyperplane, I take lots of I take transversals, and they must have isolated singularities, local system monodromy. And then there is something to remember. So I have the boundary of the Milnor fiber. And the Milnor fiber is near to the zero fiber. A part, the singular set is also part of the zero fiber. And a neighborhood of that singular set defines also a part of the boundary of F. The boundary of F and the singular set, they intersect here at the end, the Milnor ball. And then you see that here I have part of the Milnor fiber and also part of the boundary. I call this the second boundary. And later it was the other people, they find a very nice name, vanishing zone, for the neighborhood, which is a very good name, better than second boundary. And then you have, but I will call this second boundary. And then the second boundary is the union over all second boundaries for each component. So, fact, singularity with a one-dimensional singular set gives you much more structure already than an isolated singularity. There you have only a Milnor fiber, you have Milnor monodromy, and the intersection form, some other things. But here you have much more to see. So the singular point you could see in the isolated case was only a point. If you are interested in algebra, you even know that this point has an interesting algebraic structure. But in the geometry, you could see nothing, only after deforming. In the one-dimensional case, you have even more geometry and also more algebra if you want. Okay, now here these vertical monodromies, you can compute them. And so in the non-isolated case, this is this case here, A infinity, you see nothing will happen. So this vertical monodromy, there should be the identity. But in the D infinity point case, then you have to think, you have to walk around here. And this is misleading since this is a real picture. But you can show that the vertical monodromy is minus the identity. Also there, and then for this triple point, you have the three different vertical monodromies. Since the singular set has three components, and they should have the same answer anyhow, since this problem looks symmetric, and they are all the identity. And in the exercise session, we can perhaps look why. Okay, so now our attention will be on this second boundary. This second boundary, yes? Yes. Yeah, so okay, so this is a good question at the right moment. Since the Milnor fiber of the transversal section is here, and we have just a bundle over a circle with this transversal Milnor fiber as fiber, but not with the Milnor monodromy. Of course, there's also that exists, but I focus now on this vertical monodromy. And then you have the Wang sequence, which is a sequence for fiber bundles over a circle. And so the only non-vanishing part is this part. So this means that these two homology groups are completely determined by the vertical monodromy. In fact, by the eigenvalue 1 of this, the kernel and the co-kernel. And so this is clear that you have this formula from this short sequence. And of course, this has nice corollary, since if this kernel is 0, and it will happen if there are no eigenvalues 1. Okay, so this is if there are no eigenvalues 1, then also the co-kernel is 0. So then both groups are 0. Oh, could have torsion, one of them. But the rank is 0. Okay, so this is a second sequence. So the Wang sequence was first sequence. We have also a second sequence. Since we compare the second boundary with the Milnor fiber. Mostly people compare the full boundary with the Milnor fiber. But let's take only this part. And then you write down the long exact sequence. And then you know certain things, that the homology of F is 0 in certain dimensions. So after some times you can see that the only interesting part left is this sequence, this 6-term sequence. And then in the 6-term sequence you see already the 2 things which appeared in the Wang sequence. And they are on quite interesting places. So if they are 0, as this one is 0, then also the homology of the Milnor fiber is 0. And so we are looking especially for the value of H n minus F. Okay, then there are some technical things which I'm not going to explain, but they tell that this group and this group are dual to each other. And in fact, every group you see here is dual to the group which is symmetric and on a symmetric place. So these 2 are dual and also these 2 are dual. So it means anyhow that they have the same dimension but can be different in torsion. And these 2 groups, they are a kind of policemen who tell you where to go. And I've written them another, and this time in blue. And from this you already have some corollary, an important corollary about the Hn minus 1 of F. So the dimension of this guy can never be bigger than the dimension of this guy. And this guy happened in this rule, appeared in the Wang sequence. And its dimension was never bigger than the dimension of the transversal Milnor fiber. So you immediately have that this Betti number of F is never bigger than the sum of these transversal Milnor numbers without multiplicity. So I had this quite long ago, I had a kind of, not discussion, but correspondence with David Massey. Since by doing this algebraic, you get equalities which involve mostly the multiplicity of the singular set. But if you use topology, and excision in topology is something which is not a kind of algebraic thing. In fact, you can do more by doing this excision in topology and get better results. That's why I like the topology so much. Okay, so this is a kind of equality, but it's quite often much better. Quite often much better than this. Okay, so then, as soon as we are here, we can have some topological consequences. And we did not discuss Milnor's book, which is the fundamental book, almost 50 years old now, or more than 50 years old, I think even. And he has a paragraph called, is K a topological sphere? Of course, then you have to know what K is. K is the intersection of the 0 fiber with the sphere. It's called a link of the singularity, and that link is smooth in the isolated singularity case. In our case, it can have singularities. And then one of his statements is the link or is the boundary of the Milnor fiber a topological sphere? And so we have a characterization in that case by using a if you look to this, if the determinant of this vertical monodromy is plus or minus 1 for every branch, and if the determinant of the Milnor monodromy is plus or minus 1, then we have this condition is delta F a topological sphere. In Milnor's case, you had isolated singularity, then you had only this condition 3b necessary. So there were no vertical monodromies. Okay, this is just for reference. So it's not clear that you have to understand this at the moment, but it's a good reference. Okay, then in the last, how many minutes? So 20 minutes, I think. I have to do the same thing from the beginning for this non-isolated singularity business. So we are now doing deformations. And I cannot, Terry, take a generic linear form. So in this toy example, which is for s equal to 0, it's just 3 lines with 1 double line. And then I move one of these lines to the right. So I get now this picture, where here I have a non-isolated singularity. These 2 points are the easiest non-isolated singularities, which are the Whitney umbrellas. The transversal type is A1. Here I get an isolated singularity, and you can expect that somewhere in the middle there is another isolated singularity. You can also do calculus, and this is easy in this example. Okay, going back to the same theme as before, I have a start with this singularity with a one-dimensional singular set. Well, so you see here in red the singular set. This is the Milnor vibration, it's over here. Now I am going to deform, but to deform in a controlled way. So in a controlled way means that over this Milnor ball, I want to have still the same vibration over this circle and over this circle. So these are some extra conditions, and I have no algebraic criteria for that. But if you can do it, it works. And of course, you can try to write down, here are some transversality conditions anyhow. Now, we have still the same picture. We have one special point, and above this special point, I have the deformed singular set. And you see that the number of components of the singular set can change. So these two lines over here, they became one hyperbola. So the number of components can change. This is also important. And so this is all above this special point. And then there are these isolated critical points which splits off, and these are the other points. So there are 2 sets of points, singularities. One are the isolated, which split off, and the other is the non-isolated piece. Now, then you know already what is going to happen. I do the same trick, the same formula. So it means that I just take the Milnor fiber ratios above all these small disks. And for the isolated critical points, which are here, I can reduce this to the isolated singularities, which generically are perhaps Morse points. But anyhow, they are bouquet of spheres in dimension n-1. But in this middle thing, I have not a local singularity anymore. I have then a neighborhood of non-isolated singularity. So I can cut away everything which are far away from this one-dimensional deformed set, but I still keep a kind of not completely local situation. And then what we're going to do is to say, okay, I know exactly what is going to happen in smooth parts here. Since there I have, as before, these transversal singularities, and I have bundles of transversal singularities over this smooth part. But they also have special points where something could happen, special non-isolated singularities. Okay, and now we focus especially on this part E0, F0. Oh, here is written that the deformation should be good, so I forget that and go back to this picture. Also, this is the picture I discussed already. It writes down again what I said before, that they can cut away everything which is far away from the critical set. For that, it's called vanishing homology. That's the reason that it's, and far away, the homology is, the vanishing homology is neglectable. And this is then the vibration over the singular set. What you see here is part of what was written red in the other paper. So the singular set in this picture looks like pieces of surfaces. And the pieces of surfaces, they can have holes, they can have genus. So forget the singular set is one-dimensional. This is really a piece of surface. And then you can have here just a kind of singularity of the singular set. And you have a bundle with the transversal Milnor fibers everywhere, except that this bundle could also degenerate. So there are special points where you don't have the generic transversal fiber. Okay? So what we are going to do is to say, okay, everything which is not green over here, away from the red points, so this is nice. So we are bundles over, not circles, but over spaces we understand. And so we can handle them. And then they have neighborhoods of points here where we need special information, what is going to happen, and we can use them as building blocks. So we put apart those two things. We can use Meyer Viatore, so to say. And if we put them apart, just yes, then we can end up with this theorem. So I want first discuss the theorem and then say a few words how you get to the theorem. The first thing is that you find the gain from the concentration in the 2 dimensions. The second part is this looks quite a formula which is not easy to read. But it tells you that the Euler characteristic of the Milnor fiber, you can get them by taking the Euler characteristic of the special points, you see, and taking the pieces which were not green, so the pieces where we had a good vibration, Euler characteristic of that times the transversal Milnor number, and then you add up the number of spheres from isolated singularities. So anyhow, you have a formula with all the ingredients you can see from the picture. Only thing you have to know is the Milnor number of the transversal guy, how many of those points, special points, and their characteristics. So this will be easy proof. Then we can we have that is Hn of f is a quotient, so to say, of the direct sum of all homologies of transversal fibers. So we had a kind of set of the components of the singular set. Could be less even than the original one after deformation. And say we end up with one component. Then then the Milnor number, the Betti number, could never be bigger than that transversal Milnor number. And if it more components, it can never be bigger than the sum of those. Oh, it's written here. Yes, it's a corollary. And then there is some other statement about that the Betti number could also be compared with the Betti number of the Betti numbers of these of the deformed singularities. So if we go back to this picture, here where we had special points. If I know the Betti numbers of these special points, the Bn minus 1, then this is also upper bound. Say this was a d infinity point. I know this d infinity point has Bn minus 1 is 0. So as soon as I see a d infinity point, like in this case, then Hn minus 1 f is 0 for that component. So if it's irreducible. Now this is a very strong way and shows that in many cases this Betti number can be 0. Okay, about the proof I will be very short. So you just don't try to read the details. You see my torus. So you see union, and these blue things I like to know. And if I know enough about the other things and about the maps, I will be able to compute. That's all you have to remember, since I'm not going to do that computation. I will give you an intuitive way to tell you why this kind of statement was true. So the idea is that it's not completely rigorous, but it gives you a very good feeling. You want to build a big Milnor fiber. So, but then doing that, you start with a transversal Milnor fiber for every component. Now, let's look for one component. So you have then a point here, and you have the transversal Milnor fiber. Then you have to complete the fibration above the complement of the green things. So if it was a disk, you had no problems. But if you're not a disk, you have these transversal monodromies. So in fact, there are loops you have to add, fiber bundles over loops you have to add. And this fiber bundle over loops, they have this vertical monodromies. So if you have a vertical monodromy, which is not the identity, it brings down the homology of the thing you have. And also, so that means that you end up with this number which is much lower than this transversal Milnor number for each component, unless the monodromy is the identity, this transversal. There are also some genus loops which also affect. And at the end, if you plug in these special singularities, if you plug one in singularity, which is Bn minus 1 is 0, you kill all the homology. And if it's not 0, you kill it with the possibilities of killing. And that means that you get back to this theorem, that this type of things, that you get a minimum over each guy. Okay. So this is more or less what I say. Okay, then what you can do is so the idea, so let's try to say it again. After deforming, you have a situation which you have much more information. You have extra monodromies, but especially these singularities in the deformation, the special singularities, they often have a big effect on Bn minus 1. And this is the case, anyhow, if I have a one-dimensional isolated singularity with transversal type A1, this is one of my first papers, an issus or a smooth line. And then the statement was it is the homotopy type if F is a bouquet of spheres. And then since the D infinity point, if it kills the Sn-1, which was the transversal singularity, you find a bouquet of spheres in middle dimension. If the D infinity point, there are no D infinity points, you cannot kill the first guy, but you can prove anyhow this kind of statement. This was isolated line singularities. And you can apply this kind of things in other cases. And so if you go back to the original sheets of a year ago, you can read the details, but you can also make very nice pictures and make them with server and show you for fun some of those pictures. Theo de Jong also did transversal type A3. And so you see here kind of things, and then you deform, and then you look to the singularities you can see in the deformation. And this will tell you something about the Betty numbers. And so here in case B, you have killed the transversal cycle. This was something else. And then they have this nice example. Is there also a picture? No, there's no picture. So let's end with this nice picture. And thank you very much for the attention.
Any question, comment? Please use the microphone, otherwise it will not be recorded. Okay, wait a minute.
Yes, Professor Sesma, I wanted to ask, what do you mean by transversal type?
Can you repeat the question?
So, for example, in this slide, it says transversal type A3, and you write, for example, F1 A3, F2 A3. What does transversal type mean in this case?
I did not understand your...
What do you mean by transversal type
Yeah, you
A3?
understood the question? So it's
I think he asked what you mean by transversal type A3. Is that the question?
Yes, that's it. Thank you very much.
okay. Yes, transversal type A3 is just like here. So if this was a line, and the singular set was the x-axis. So then just here I have a x is just a number now, a scalar. So I have z squared plus y squared z, two variable singularity, and this is equivalent with A3. And I have the other here, where this is the singularity, which is equivalent to y to the power 4 plus z squared. And this is also another form of A3. And it turns out that if you look to this as a non-isolated singularity, these are the two, so to say, codimension 1 singularities in this case. In the transversal A1 singularity case, you had only one codimension 1, and which was the D infinity. Here you have two of them, and they behave slightly different. Other questions?
More questions? Okay, go ahead.
So all the things you do with the singular locus of the zero fiber of the original variety, right?
Yes.
So how can you have isolated points in these? Some pictures ago, you had some isolated points that you take out to have a vibration over the singular set. How can you have something isolated if you have a germ? Maybe I missed something.
So what you want is deformations which keep the situation over the big ball equivalent as before. That means that your intersections of the singular set with infinity, with the sphere, they have to be equivalent. But as in this example, it's if you start moving this, then and anyhow some isolated singularities could appear. And of course, there is sometimes a question if what happens if they don't appear. If you have a nice deformation and without extra points, and there are still some open questions there. Is then a topological trivial, yes or no, or can be different?
Okay, thank you.
More questions, comment? Okay, let's thank again the speaker.
And I hope to meet you during this exercise session. And the exercises are not too difficult. And if Mihai is listening, I say hello to him.
Okay. So just to remind you, if you want to join us in the happy hour, please pay in the main desk, in the main entrance, 10 reais. Oh, sorry. Yes, 10 reais or $2 more or less for a student, and 50 reais or more or less $10 for researcher. Okay, just pay in the main desk. Thanks. See you. Do you want to say? Oh, wait, sorry. Queria falar alguma coisa? Okay, about the restaurant, if you want to find some, you can ask, okay, let me see. Who is the student that will support, the team of students that will support the committee? Please raise your hand. Okay, could you come here, please? Okay, come here, come here. So this is the team of students, graduate students that can help you in time. Okay, I will ask them to introduce themselves itself, and if you want to go to a restaurant, please, they can help you. Please introduce yourself. Just your name is fine.
So good morning. My name is João Paulo.
My name is Tiago.
My name is Maíra.
My name is Abraham.
And I am Ellen.
Hello.
So if you want, for instance, ask them how to go to a restaurant, please do that. Okay, then any help, please don't hesitate to ask any of them and ask me. Okay, see you later. Bye.